Hello everyone, welcome back to MP Coding's Linux device driver development series with Raspberry Pi. In today's video, we will discuss the Linux kernel poll and select mechanisms. This video is a continuation of the previous lesson. If you are new to this topic, I recommend watching the previous video first, where we discussed wait queues and blocking I/O, because today's topic builds directly on that concept. The poll and select mechanisms are user space system calls that allow a single process to monitor multiple file descriptors at the same time. Instead of waiting on just one file descriptor, a process can give the kernel a list of file descriptors and ask to be notified when any one of them becomes ready for I/O. This allows the process to sleep efficiently until an event occurs, without busy waiting and without creating a separate thread for each file descriptor. This is the standard design used in event-driven applications. Instead of blocking on read, which waits on only one file descriptor, or continuously retrying operations that return -error again, the application simply passes a set of file descriptors to the kernel and sleeps until at least one of them becomes ready. From the driver side, both poll and select are implemented using the same mechanism. They rely on the .poll file operation, which is typically implemented using a wait queue to notify the kernel when the device becomes ready. Now that we understand the concept, let's move to the driver code. This is the same code we implemented in the previous video, where we introduced wait queues for handling blocking behavior. In the last video, we implemented a wait queue to handle blocking and non-blocking behavior. The logic was simple. When the read function is called and data is not available, the driver first checks whether the file was opened in non-blocking mode. If the file is opened with the O_non-block flag, the driver immediately returns -error again. If the file is opened in blocking mode, the process is put to sleep using the wait_event_interruptible function, and it stays asleep until the data becomes available. When the button interrupt occurs, the ISR sets data_available to 1 and wakes up the sleeping process. Then the read function resumes execution, resets data_available back to 0, copies the message to user space, and returns the copied message size. That is exactly what we implemented in the previous video. If you did not clearly understand how wait queues work, please watch the previous video first, where I explained why we should use wait queues instead of busy waiting loops. Now let's start implementing the poll file operation. First, open the file_operations structure definition. Here we can see the poll file operation prototype. Let's copy this definition. Now go back to the source file and paste it into our driver. Next, change the function to static and name it my_poll. The function has two parameters. The first parameter is the file structure pointer, and the second parameter is a poll table structure pointer. This poll table is used by the kernel to register the wait queues that the process should wait on. Inside the function, the first thing I will do is print a message to the kernel log indicating that the poll operation was called. Next, we need to register our wait queue with the poll table. For that, we use the function poll_wait. This function takes 3 arguments: the file pointer, the address of our wait queue, which is my_wait_queue, and the poll table pointer. This step does not put the process to sleep. It simply registers the wait queue, so the kernel knows which queue should wake the process if an event occurs. Next, we check whether data is available. You can see that the poll function returns a type called __poll_t, which is essentially an unsigned integer used as an event mask. So we create a local variable called mask, initialize it to 0, and then update it depending on the device state. If data is available, we set the mask with the epoll_in and epoll_rd and ORM flags. This flag indicate that the associated file descriptor is ready for reading. And this flag means normal data is available to be read. Finally, we return the mask value. If no data is available, the mask remains 0, which tells the kernel that the device is not ready for I/O yet. So now the poll implementation is complete. The final step is to register this function in the file_operation structure. So we add the entry .poll equals my_poll. And now our driver supports poll and select mechanisms from user space. Okay, let's save the file and build the module. Type make and hit enter. Okay, build was successful. Now let's create a test application to verify the poll implementation. Here I created a file called test_poll.c. Currently, this program only opens the device file and then closes it. Inside the main function, the program simply opens the device file provided as a command line argument, using read-only mode. If the open operation fails, it prints an error message and exits. Otherwise, it just closes the file descriptor and returns. Now let's extend this program to use the poll mechanism. First, we include the poll.h header file because it contains the definitions required for the poll API. Next, after opening the file descriptor, we declare a structure called poll.fd. If you look at its definition, this structure contains 3 fields. The first field is the file descriptor that we want to monitor. The second field is events, which specifies the type of events the application is interested in. The third field is our events, which is filled by the kernel and indicates which events actually occurred. Now let's initialize this structure. I will name this as pfd. We set the fd field to the file descriptor we just opened. Then we set the events field to poll in, which means we are interested in knowing when the file descriptor becomes ready for reading. The events field will be filled automatically by the kernel when the poll call returns. Now we create a loop that continuously waits for events using the poll system call. Inside the loop, we call the poll function. This function takes 3 arguments. The first argument is the address of the poll FD structure. The second argument is the number of file descriptors we are monitoring. In this case, it is just 1. The third argument is the timeout value. If we set it to -1, the poll call will wait indefinitely until an event occurs. The poll function returns 0 if a timeout occurs, and -1 if an error occurs. Let's save that return value in int_ret variable. So if the return value is less than 0, we print an error message and exit the loop. If poll returns successfully, we then check the return events field to see which event actually occurred. In our case, we check whether the poll in event is set. If it is, that means the device is ready for reading. Then we call the read function to read data from the device. We need memory to store the data from device, so here before the while loop, I will create a buffer array that will store the message received from the kernel driver. A buffer size of 64 bytes is sufficient for our example. Okay, now pass the buffer pointer here, and then set the size of the buffer going to read. If the read operation fails, we print an error message and exit. Otherwise, we terminate the buffer with a null character and print the received message to the console. Finally, before entering the loop, I will add a simple message that says, waiting for button press. Press Ctrl+C to exit. So this program will continuously wait for poll events, and whenever the button interrupt occurs, the driver will signal that the device is readable, and the program will read the message from the device and print it to the console. This is a simple example of how poll can be used to efficiently wait for device events without busy waiting. Now let's see this implementation in action. First, build the test application using GCC. The build is successful. Next, open a new terminal and monitor the kernel log buffer so we can see the messages printed from the driver. Here in this terminal, load the kernel module. The module loads successfully, and the device node is created in the /dev directory as my_c_dev0. Now let's run the test application and pass /dev/my_c_dev0 as the input parameter. After executing the program, we can see in the kernel log that the device was opened. Immediately after that, the poll function is called. In the terminal running the test application, we also see the message, waiting for button press. Now let's understand what happened internally. In the test application, the program first opens the device file, which triggers the device my_open in the driver. Then it prints the device open message to kernel buffer. After that, in the user space app, then prints the waiting message to the console. After that, the program enters the while loop and calls the poll system call. Inside the kernel, this triggers our my_poll function. The driver then registers its wait queue using poll_wait and checks whether data is available. Since initially data_available is 0, the driver returns 0, which means no event is ready. At this point, the user space poll call goes to sleep, waiting for any registered event to occur on the file descriptor. Now let's press the button. In the kernel log, we can see the message GPIO interrupt occurred, which means the interrupt service routine was triggered. Inside the ISR, the driver sets data_available to 1 and calls wake_up_interruptible. This wakes the processes waiting on the wait queue. Because the poll mechanism registered this wait queue earlier, the kernel now re-evaluates the poll condition, which is why we see another poll called message in the kernel log. Now inside my_poll, the driver sees that data_available is 1, so it sets the event mask with the readable flags and returns that mask. Back in the user space application, the poll call exits because an event occurred. The program then checks which event was returned, and it sees that the poll in event occurred, meaning the device is ready for reading. So the application calls the read function. On the driver's side, this triggers the my_read operation, which prints the read called message. Since data_available is already 1, the driver does not enter the blocking section. Instead, it resets data_available back to 0, copies the message to user space, and return. Back in the test application, the message is copied into the buffer and printed to the console. After that, the program continues the while loop and calls poll again, repeating the same process. If I press the button multiple times, the same sequence happens again and again. Now, if we want to exit the program, we can simply press Ctrl+C. When we do that, the process receives a signal, the poll call is interrupted, and the program exits. In the kernel log, we can see the poll called message once more, followed by the device closed message, indicating that the file descriptor was closed and the process terminated cleanly. With this method, you can see that we never enter the blocking section inside the driver. Because we are using polling, the driver does not need to explicitly put the process to sleep like we did with the wait queue inside the read function. Instead, the driver simply registers its wait queue with the poll mechanism and reports the device state when the kernel asks for it. Whenever new data becomes available, the driver wakes the wait queue, which notifies the polling process that an event has occurred. At that point, the user space application wakes up, detects that the device is ready, and then calls read to retrieve the data. So the driver does not block waiting for data. Instead, it simply signals the user space application when data is ready, and the application decides when to read it. Here, this flowchart shows what happens during the entire process. Take a moment to look at it as well. So poll_wait does not put the process to sleep by itself. What it actually does is register the driver's wait queue with the kernel's poll infrastructure. This allows the kernel to know where the process should be woken up from when an event occurs. The actual sleeping and waking of the process is handled by the kernel's poll mechanism, not directly by poll_wait. I have also included a table that shows the return mask values used in the poll mechanism. Please take a look at that as well. I will upload this file to the GitHub repository so you can easily reference it later. Now let's look at the select method. Both poll and select perform the same job. They allow a user space application to wait for events on file descriptors. From the driver's perspective, the implementation is exactly the same. Both system calls rely on the same .poll file operation in the driver. The only difference is in the user space API used by the application. To demonstrate this, I created another user space test application that uses the select system call. First, we include the sys/select.h header file, which provides the select API. Inside the while loop, we declare a variable of type fd_set, named read_fds. Next, we clear the set using the fd_0 macro. This ensures that the file descriptor set starts empty. Then we add our device file descriptor to the set using the fd_set macro. After that, we call the select function. I'm not going to explain what these parameters are. You can search on the web. In this call, the timeout parameter is set to null, which means the application will wait forever until the file descriptor becomes ready. If select returns a negative value, it means an error occurred, so we print the error message and break out of the loop. If the call succeeds, we then check whether our file descriptor is ready for reading using the fd_is_set macro. If it is ready, we simply call read, just like we did in the poll example. The rest of the logic is almost identical to the poll implementation. The only important difference is that with select, we must rebuild the file descriptor set before every call, because the select function modifies the set internally. Now let's build this test application. Compile it using GCC. Okay, build completed successfully. Now let's run the program. When we execute it, you can see that it behaves exactly the same as the poll example. The application waits until the button is pressed, and once the device becomes readable, it receives the message from the kernel driver and prints it to the terminal. So from the driver's perspective, there is no difference between poll and select. Both mechanisms use the same .poll file operation in the driver and the same wait queue infrastructure inside the kernel. The only difference is how the user space application waits for the event. Now let's look at the differences between the select and poll methods. First, in select, we use 3 separate fd_set bit masks. One for read events, one for write events, and one for exception events. In contrast, poll uses a single array of struct poll fd, where each entry represents a file descriptor along with the events we want to monitor. Next, consider the maximum number of file descriptors. With select, the number of file descriptors is limited by fd_set size, which is usually 1024 on most systems. However, poll does not have this hard limit, so it can scale better when working with a large number of file descriptors. Another important difference is how the file descriptor sets are handled. In select, the FD sets are modified by the kernel, so the application must rebuild them before every call. In poll, the events field remains unchanged, and the results are returned in the events field, so the original configuration does not need to be rebuilt each time. There is also a difference in the timeout format. In select, the timeout is specified using a struct timeval, which provides microsecond resolution. In poll, the timeout is simply an integer value in milliseconds. Because of these design improvements, poll is generally preferred for new applications. Select is an older interface and has the fd_set size limitation, but it is still widely used and supported on almost all systems for compatibility reasons. Now, the real power of poll and select is their ability to monitor multiple file descriptors at the same time. In our current test program, we are only monitoring one file descriptor, so it does not really demonstrate that capability. To properly demonstrate this, I am going to open multiple instances of the same device driver. However, with our current implementation, this will not work correctly. That is because we are using a single global variable called data_available, which is shared by all file descriptors. So if multiple processes open the device, they will all share the same state, which is not ideal. To solve this problem, we will introduce private data for each file descriptor instance. I have already explained how to implement private data in a character device driver in another video on my channel. If you are not familiar with that concept, please go and watch the character device private data video first. Here, I will just show the necessary changes, without going into too much detail. First, remove this data_available variable, and add a global event counter that tracks how many interrupts occurred. Every time an interrupt occurs, this counter will increase. Next, I will create a structure for the private data of each file descriptor. This structure stores the last event number that a particular file descriptor has seen. When the device is opened, we allocate memory for this structure. Here we allocate memory using kmalloc, initialize the structure, and store the pointer in file private_data. This ensures that each open file descriptor has its own private state. Since we allocated memory, we must also free it when the device is closed. So inside the release function, we add kfree and pass the private data field. This ensures there are no memory leaks. Next, we update the interrupt service routine. Instead of setting data_available, we simply increment the event counter. Now every interrupt increments the event counter and wakes all waiting processes. Now let's update the read function. First, we retrieve the private data from the file structure. If the event count has not changed, it means no new data is available for this file descriptor. Once an event is available, we update the private event value and copy the message to user and return the message size. Finally, we update the poll implementation. Again, we retrieve the private data from the file structure. Then we register our wait queue using poll_wait. Instead of checking data_available, we check whether event_count is different from last_event. If they are different, it means a new event has occurred, so we return the poll event mask. This tells the user space application that the device is ready for reading. With this approach, each file descriptor tracks its own event state. So now, if we open the device multiple times, each instance can independently detect new events, which makes the poll/select demonstration much more realistic. Here, this also needs to update. Let's build the module. Okay, build was successful. To properly demonstrate the real advantage of poll, I created another test application that opens multiple file descriptors. In this example, I open two instances of the same device. Each open call creates a separate file descriptor, and because we implemented private data in the driver, each instance now tracks its own event state. Next, I create a struct polfed array with 3 entries. The first entry is standard input, which allows us to monitor keyboard input from the terminal. The second and third entries are the 2 device instances we opened earlier. For all 3 file descriptors, I set the event type to poll in, which means we are interested in readable events. I also added some console messages so we know what to expect when the program runs. Now let's look at the main loop. Inside the loop, we make a single poll call. This call monitors all 3 file descriptors simultaneously. Here, the number of file descriptors is 3, and the timeout value is -1, which means wait forever until an event occurs. Once poll returns, we check each file descriptor independently. First, we check the standard input. If the user types something and presses enter, the program reads the input and prints it with a message indicating that it came from stdin. Next, we check the first device instance. If it becomes readable, we call read and print the message received from the driver. Then we do the same for the second device instance. This clearly demonstrates how one process can monitor multiple event sources at the same time. In this case, the program can respond to keyboard input from stdin and interrupt events from 2 separate device instances, all using a single poll call. Finally, when the program exits, we close both file descriptors to clean up the resources. Now let's build this test application using GCC. Okay, build completed successfully. Next, open another terminal and monitor the kernel log buffer so we can see the driver messages while the program runs. After that, load the kernel module. The module is loaded and device node has been created. Now let's run the test application, passing the device path as the argument. Now you can see that 2 device instances are opened, and the poll function is called for both devices. The kernel log shows this clearly. This means both file descriptors are registered with the poll mechanism. Now let's type something in the console and press enter. You can see that the console prints the same message we entered. That happens because the std event occurred, so poll returns. The program enters the first condition, reads from standard input, and prints the message. Since no device event occurred, the other checks are skipped, and the program goes back to the loop and waits again in poll. Now let's press the button. In the kernel log, you can see that 2 separate poll events occurred, and 2 read calls were executed, one for each device instance. So from the device driver side, everything is working exactly as expected. However, in the console, we should see 2 messages printed, one from each file descriptor. But initially, nothing was printed even though the read calls were executed in the kernel. The issue was actually in the test application. In the printf statements, I forgot to include a new line character at the end of the message. Because of that, the output remained in the buffer and was not flushed to the term. So I added a new line character to both printf statements, rebuilt the program, and ran it again. Now when I press the button, you can see that the messages from both open device instances are printed correctly in the console. So this example demonstrates how poll can monitor multiple file descriptors simultaneously and how a single application can handle multiple device events efficiently. This is it for today's video. If you have any questions, feel free to leave them in the comment section. Today we discussed how the poll and select mechanisms work in the Linux kernel, how a driver implements the .poll file operation using wait queues, and how user space applications can monitor multiple file descriptors efficiently. In the next video, we will discuss asynchronous notification using fasync, which allows the driver to notify user space processes when new data becomes available. So stay tuned, and see you in the next video.